Last time we had a look at the Simpsons 1/3 rule. In actual fact, there is another Simpsons rule known as the Simpsons 3/8 rule, which we'll have a quick look at in this short video, and then we'll go on to generalize this concept and discuss briefly the Newton-Cotes formulae for integration. So fitting a quadratic to 3 points and integrating yields Simpsons 1/3 rule, which is given by that expression there. We can use multiple pairs of intervals, and using this gives us the composite Simpsons 1/3 rule. So we split it up into pairs of intervals. We do each interval separately using Simpsons 1/3 rule and sum the results to get a formula that looks like that. Can we do better than Simpsons 1/3 rule? Why not fit a cubic polynomial to 4 equally spaced x values? So we choose x1, x2, x3, and x4. We calculate the function values at those points, and we fit a cubic polynomial between them. The cubic, generically, can be written as p of x is equal to ax cubed plus bx squared plus cx plus d. Then we approximate the integral of f of x as the area under the cubic polynomial p of x. Mathematically, we write that I is equal to the integral of f of x from x1 to x4, and that's approximately equal to the integral of p of x dx from x1 to x4, where now we plug in for this polynomial that generic cubic we had previously, ax cubed plus bx squared plus cx plus d. We can integrate this analytically. We get that expression there. We evaluate it at the endpoints. We won't go through the detail because it's messy and it's just algebra, but it's quite straightforward to show that this integral, the integral of the polynomial, can be written as x4 minus x1 divided by 8 multiplied by the function value at x1 plus 3 times the function value at x2 plus 3 times the function value at x3 plus the function value at x4. We reintroduce h. H is just the mesh spacing, and here it's given by x4 minus x1 divided by 3. If we substitute that up there, we can write that I is equal to 3h on 8 multiplied by this sum of terms. This is Simpsons 3/8 rule. Obviously it's called 3/8 because of that coefficient there. We can actually go away again and estimate the truncation error in Simpsons 3/8 rule, and we can show that it's approximately given by this expression. The error is equal to negative 3/80ths, the fourth derivative of our function evaluated at some psi in the interval, multiplied by h to the fifth, and using our order notation, that's just equal to order h to the fifth. So just like Simpsons 1/3 rule, halving h gives us 1/32 the error. So Simpsons 1/3 rule and Simpsons 3/8 rule have the same order of accuracy, h to the fifth. Again, we would never use Simpsons 3/8 rule just with 3 intervals. We'd split it up into triplets of intervals and do each set of 3 intervals using one application of the 3/8 rule. So for example, if we had the function across here, the coefficient multipliers would be 1, 3, 3, 1. Then for the next set of intervals, they'd be 1, 3, 3, 1, etc. And we can see that this point here has a contribution from both of these sets of terms. This point here has a contribution from both of them. And if we then just collect all these terms, we can write the composite Simpsons 3/8 rule as I is equal to 3h on 8 multiplied by this somewhat complicated set of sums. So the first group is multiplied by 3 and its I is equal to 2, 5, 8, 11, etc. The second set group is also multiplied by 3. Those are points where I is equal to 3, 6, 9. And finally, another set of points where a multiplier is 2. These are given by the points I is equal to 4, 7, 10. This formula is applicable when we have ordered our points as going from x1 to xn. This is a messy formula, and the number of segments must be a multiple of 3, and you're much less likely to get something being a multiple of 3 than you are getting something to be a multiple of 2. In actual fact, because the order of accuracy is the same for both of these Simpsons rules, it's easier and just as accurate to use Simpsons 1/3 rule. However, how do you use Simpsons 1/3 rule if the number of segments you're given is odd? Well, the way in which to do that is to combine Simpsons 1/3 and 3/8 rules as we have done in this figure. So in this particular figure, we have only 5 intervals, and we would treat the first pair of intervals using Simpsons 1/3 rule and the last 3 intervals using Simpsons 3/8 rule. So if we have multiple segments, but the number of segments is odd, for all of the initial segments except the last 3, we would use Simpsons 1/3 rule, and just for the last 3, we would use Simpsons 3/8 rule. This then gives us an integration that has the same order of accuracy, that order h to the 5th. So we have seen that we can fit a straight line to pairs of points and integrate, that's the trapezoidal rule, quadratics to triplets of points, that gives us Simpsons 1/3 rule, and cubics to sets of 4 points, which gives us Simpsons 3/8 rule. Is there anything stopping us at cubics? Well, the answer, of course, is no. We can fit higher and higher order polynomials to the data points, and the next one in these series is fitting a 4th order polynomial to 5 points, and that is known as Boole's rule. You can see here that the coefficients 7, 32, 12, 32, 7 look like they're starting to get fairly complex. The error in this case is order h to the 7, so it is more accurate than the 2 Simpsons rules. But recall that as we start fitting higher and higher order polynomials, we start getting excursions of the polynomial from the underlying data. So we start getting wiggles, and if we integrate these wiggles, which aren't real, we will begin to get larger and larger errors. So you would never ever go beyond Boole's rule, and in actual fact I would recommend that Simpsons 1/3 rule, except for the case of the odd number of segments, is probably as higher order as you would want to go. But collectively, these formulae here are known as the Newton-Cotes formulae.